In our discussion of vectors in the plane, we distinguished two vectors in particular, and we distinguished I, which was going to be a 1 unit change horizontally from left to right. And likewise, we picked another vector j that was going to be a 1 unit change vertically now from bottom to top. Now, what these two vectors let us do was to really take any vector v that we had in the plane, and we could write that vector v as a sum of our i's and j's, assuming that we scaled them appropriately, so that we could have this vector v being alpha times I plus beta times j. And then if we set up a convention where we were going to have an ordering to our i's and j's, where I was going to come first and j was going to come second, then we could come up with a component form where we didn't need to write the i's and j's anymore. We could just write the components. Alpha was going to be the component for I, and beta was going to be the component for j. Then what we wanted to do in Calc 3 was to kind of bump this up to 3 dimensions. So what we did was we took our plane and we had our I coming off in this direction, we had our j coming off in this direction, and so we picked another distinguished vector k that was going to be perpendicular to our plane containing i's and j's. And so this let us come up with a new distinguished set. A new distinguished set of our I, j's, and k's, which again we'll kind of go ahead and choose an ordering for that. That was going to be I was first, j was always going to be second, and k then was going to be third. And so just like before, we could take any old vector v that showed up in 3-dimensional space, and we could write that as the sum of i's, j's, and k's scaled appropriately. And with respect to our ordering I, j, k, we could again do the component form, alpha being the component of I was first, beta being the component of j was second, and gamma being the component of k was going to be third. So now we want to generalize this. So for any positive integer n, what we're going to do is to take a new set, and this new set is going to be e1 hat, e2 hat, all the way up to e sub n hat. And we want to take all possible sums of all possible scalings using real numbers. And so what this will give us is a new set of vectors Rn, which is just going to have the following form: alpha 1 e1 hat plus alpha 2 e2 hat plus all the way up to alpha sub n e sub n hat, where our only requirement is that alpha 1, alpha 2, all the way up to alpha sub n are real numbers. So that if we have any particular vector in there, so if we take a v that's in there, where it's alpha 1 e1 all the way up to alpha n en hat, Then with respect to this ordering, kind of the natural ordering that we're going to put on it, so E1 hat is first, E2 hat is second, all the way up to E sub n hat being last, we can write our component form alpha 1, alpha 2, all the way up to alpha sub n. And so kind of this ordering this set of distinguished vectors that we have, we give those kind of a name, and that set is called the standard basis. And so now if we take any two vectors, say v and w, that are in this brand new set, then for v that looks like, just write it in component form, alpha 1, alpha 2, all the way up to alpha sub n, and w, who is in component form, beta 1, beta 2, all the way up to beta sub n. Then we say that those two vectors, v and w, are going to be equal if and only if the individual components are going to be equal. So we need alpha 1 equal to beta 1, alpha 2 equal to beta 2, all the way up to alpha sub n equal to beta sub n. So now as it stands, we can't really do much with our vectors. They're really just sets. And so let's put on an operation of vector addition. And so if we take two vectors, say v and w, that are in this vector space R sub n, where let's say that v looks like alpha 1, alpha 2, all the way up to alpha sub n, and w looks like beta sub 1, beta sub 2, all the way up to beta sub n. Then let's say that the sum of those two vectors, v and w, is really just going to be the sum done component-wise. So alpha 1 plus beta 1 is the first component, alpha 2 plus beta 2 is the second component, all the way up to alpha sub n plus beta sub n is our last component. And so with this, we have defined the operation of vector addition. So now we can do a similar thing with our operation for scalar multiplication. If we take a vector in here, so we've got v in Rn, where, again, we assume that v in component form looks like alpha sub 1, alpha sub 2, all the way up to alpha sub n. Then for any constant c that we're going to take from the real numbers, we're going to define c times v to be the vector that we get when we just take c times each of our components. So we've got c times alpha 1, c times alpha 2, c times alpha 3, all the way up to c times alpha sub n. And with that, we have defined our operation of scalar multiplication. So now once we have these operations defined, they're going to have some nice properties to them. And so if we look at the properties of vector addition, the first couple are really just kind of, should be pretty familiar. That if we take v and w in our vector space R to the n, then v plus w is going to give us the same answer as if we did W plus V. And so this is our commutativity. For B, if we have V, W, and U in our vector space, and if we do the operation where first we had U and V and then add W, then we'll get the exact same answer as if we did V plus W first and then added on U. And so this one is just our associativity. Now, how do we know these properties hold, or how do we actually get them from that? These are basically inherited. So they're inherited from the properties of real numbers and the fact that operations are done component-wise. Then for our third property, we've got something called the zero vector, and the zero vector is really just going to be the vector whose all of its components are going to be 0. So that thing is a vector in R sub n, and what we've got for any other vector u in Rn, if we do u plus this 0 vector, nothing happens, and we get u back, and it works the other way as well. So if we do 0 plus u, so we've got the existence of an additive identity. And then finally for our last property, if we take any element v in our vector space, then quite naturally there's an element negative v in our vector space, where for v looking like alpha 1 all the way up to alpha sub n, then minus v looks like the vector that we get when we just change the signs of all of those components. So minus alpha 1, minus alpha 2, all the way up to minus alpha sub n. Then these have the nice property that they annihilate one another under vector addition. So v plus negative v is going to give us the 0 vector, and likewise doing it the other direction also gives us the 0 vector. And so this gives us the existence of additive inverses. So now to kind of put these properties into a larger perspective, first we had commutativity of addition. Then we had associativity of addition. From there we added on the existence of an additive identity, and finally existence of additive inverses. So these last three properties taken together give us a mathematical group and then when we throw in all four properties, we get an abelian group. So this kind of puts a lot of our properties in the larger context of other objects in mathematics. Then we'll also have some familiar properties for scalar multiplication. And so if we have, let's see, A, B, C, D, E, for two vectors v and w in R to the n. And if we take any scalar c, that's a real number, then we have our distributive properties, one of our distributive properties, so that if we have c times the sum of our vector v plus w, then that gives us c times v plus c times w. Then if we have two scalars, so if we have c and d that are just real numbers, and for a vector v in R to the n, if we do c plus d times our vector v, then we get distributivity over scalars. So that's going to be c times v plus d times v. Then our associativity still holds. So likewise, for c and d that are scalars, and v, our vector, then if we do c times d times v, then that's exactly the same thing we would get as if we multiplied our scalars first and then multiplied v. And finally, for our last property, quite naturally, if we have 1 times any vector v, well, that's just going to turn around and give us v for v, any vector that we want. And kind of once again, these properties basically follow from the properties of real numbers and the fact that scalar multiplication was at least defined component-wise. So up to this point, we have kind of talked about our vector addition and scalar multiplication, but one of the two things that we were supposed to get from vectors was magnitude. And so we need to talk about how do we get the magnitude of one of these vectors. So if we take our v in R to the n, and if we suppose that that v looks like alpha 1, alpha 2, all the way up to alpha sub n in component form, then our notation for the magnitude of v, so we'll kind of put these two vertical bars by it, that's going to be the magnitude of v, and it will just be defined as the square root of the sum of the squares of all of the components. And so this really just mimics exactly what we had for dimension 2 and for dimension 3 when those were just defined in terms of our distance formula. So it just kind of extends that definition when we talk about magnitude. So this kind of gives us a pretty good introduction to our finite dimensional vector spaces R to the n. So more about those operations later.